Hello and welcome back everyone to YOLO Basic Terminologies. In the previous video, we talked about the architecture of YOLO, and in this video, we'll be talking about the matrix used in YOLO literature. So first, let's look at what a bounding box is. A bounding box, in essence, is a rectangle that surrounds an object and specifies its position, class, and confidence. So for example, if you have an image and if you want to localize an object inside the image, we need the position of the object, and we need the class or label, and we need a confidence. Confidence means how likely it is the object is to be at that location. So what are the conventions used in specifying a bounding box? So there are two main conventions followed when representing bounding boxes. The first one is specifying the bounding box with respect to the coordinates of its top left and bottom right point. So this is with respect to the position, and in order to identify the position of an object, we have to use the rectangular box, and that rectangular box can be defined by coordinates. And the way we represent those coordinates can be, there are two conventions in which we can specify the coordinates for that position. So the first one is just using the top left corner and the bottom right corner. And the second one is by using the center of the rectangle and the width and height. So these are two images showing us the two conventions. So the first one is using the top right and the top left and bottom right corners. And we can also see the confidence in the class. And the confidence is given as a float point between 0 and 1. And on the right side, we can see that we are using the center point and the width and the height of the object. And we also can specify the confidence in the class. So let's dig deeper onto the conventions that are followed and the parameters that are used to define a bounding box. So the first one is a class. A class is just an object that's inside the box. So it can be a car, a truck, or a person. And the first point, x1, y1, according to the first convention, is the x and y coordinates of the top left corner of the rectangle. And x2 and y2, according to the first convention, are going to represent the x and y coordinates of the bottom right corner of the rectangle. And according to the second convention, we can represent the position by using the center points, xc and yc, which correspond to the x and y coordinate of the center of the bounding box. W represents the width of the bounding box, and height is just the height of the bounding box. And finally, we have confidence, which indicates how likely the object is actually present in that box. So if we have a rectangular box, how likely it is that object is located within that box. So for example, a confidence of 0.9 would indicate that there is a 90% chance that object actually exists in that box. So these are all the parameters we need. So the class, the confidence, and the position coordinates. So for the coordinates, we have seen two conventions. And one is we can use the top left and bottom right corners. And the second one is we can use the center point and the width and height. So if we want to convert between the two conventions, so for example, if someone gives us the top left and bottom right corner points and we want to convert them into the center points and width and height, we can definitely do so by using this formula. So first we have to find the sum between the x coordinates of the top left and bottom right. So for example, in order to find the center point xc, we can add x1 which is the x-coordinate of the top left corner point, plus x2, which is the x-coordinate of the bottom right corner. Then we add them and then we divide by 2. So that would be the midpoint of in the x direction. And in the y direction, we also add y1 and y2 and then divide that by 2. And in order to find the width, we find the difference between the x-coordinates. And in order to find the height, we just find the difference between the y-coordinates. So once we understand how bounding boxes work and the parameters that are used to represent a bounding box, let's talk about IOU, which is intersection over union. And it's a term used to describe the extent of overlap between two boxes. The greater the region of overlap, the greater the IOU. So mathematically, it can be represented as the ratio between the intersection and the union between two rectangular bounding boxes. So according to the figure at the bottom, here A and B are our object masks, and A intersection B is the overlap between these two boxes, and it indicates the area which is the intersection of both of the masks, and A union B indicates the total area of the figures. So the total area by combining the two boxes. So if the IOU is very close to 1, then we can say that our model is perfectly overlapping the object. So in this picture, we can see that the red one might be the ground truth box, and ground truth means the label. So we need a label and a prediction in order to identify an object. So the ground truth box is the box that we label for the image, and the predicted bounding box is the one that we're going to learn in order to fit the object once the model is being trained. So if the red box represents the ground truth box and the green box represents the predicted box, if the overlap between the two is very close to 1, then we can say it's very excellent, which we can see on the right side. And if the IOU is very close to 0, we can say it's a very poor detection and our model didn't predict the object coordinates at all. So what we're trying to do in YOLO is just rearranging and changing the size of the bounding box so that it better emulates the ground truth box. So let's look at this example. For example, in the image below, we have a green box and a blue box. The green box represents the correct box and the blue box represents the prediction from the model. And the aim of this model would be to keep improving its prediction until the blue box and the green box perfectly overlap. That means the IOU between them is equal to 1. So the green box perfectly depicts the cat, but the blue box is just a prediction, and it has to learn so that the IOU between the two boxes could be equal to 1. So that's our goal. So how to calculate the IOU between two boxes? So let us assume that box 1 is represented by the coordinates x1, y1, x2, and y2, and box 2 is represented by the coordinates x3, y3, x4, and y4. So I've used different colors to represent the two box coordinates. And we will use this convention later to calculate the areas. So as you can see from the figure, x1 and y1 are the top left corners of box 1, and x2 and y2 are the bottom right corners of box 1, and x3 and y3 and x4 and y4 are just the top left and bottom right corners of box 2 respectively. So how to calculate the area of intersection? So the area of overlap between these two boxes is the one that's shaded in between, and we can represent the coordinates of the top left and bottom right corners of this overlapping region by using the coordinates x inter y, y inter y, x inter 2, and y inter 2. And these represent just the points, the corner points of the overlapping region. And let's start by defining the reference coordinate system. And we use the computer graphic convention that the positive x-axis means as we move to the right, we're moving across the positive x-axis. And when we move downwards, we're moving in the positive y direction. So to calculate the top left corner of the intersection region, we have to compare the top left corners of each of the boxes. So in order to get the top left corner of the intersection region, we have to consider the top left points of box 1 and box 2. So in this case, x inter 1 will be the x coordinate of the intersection region, and it will be the maximum of the x1 and x3. So we can see from the examples below that x inter 1 can be found by trying to figure out which box has its top left corner moved to the right. Maximum across the x-axis means the one which is further to the right. So we compare x1 and x3, and x3 is a little bit further to the right than x1. So we choose x3 for our intersection region. And in order to figure out y inter 1, can be found by seeing which box has its top left corner lower than the other. So the top left corner y coordinates for the overlapping region can be found by considering y1 and y3, and we take the maximum point y3 as y inter 1, which means we're considering the point that's further downwards. So we just considering the top left corners for now in order to figure out the top left corner of the overlapping region, and we have to use the maximum function in order to figure out the coordinates. And in order to calculate the bottom right corner of the intersection, we compare the bottom right corners of each of the boxes. So the bottom right corner of box 1 is x2 and y2, and the bottom right corner of box 2 is x4 and y4. So we compare the x coordinates for the bottom corners of the two boxes. So in this case, in order to figure out x inter 2 can be found by seeing which box has its bottom right corner more to the left. So when we compare the x coordinates initially, for example, x2 and x4, x2 is located a little bit to the left of x4, so it's the minimum point. So we're considering the minimum point for the bottom right corners, and we're considering the maximum point when we're considering the top left corner of the intersection region. And in order to get the y coordinate for the intersection, we can use y2 and y4, and we take the minimum point. And since y2 is located a little bit further upwards than y4, then we can consider y2 as y inter 2. So now we have 4 points, x inter 1, y inter 1, x inter 2, and y inter 2, which are going to be the coordinates, the x and y coordinates of the overlapping region. So boxes can intersect in many different ways. We just considered one use case. So they might be intersecting in this manner, or the one on the right side. Box 2 can be on the right side and box 1 can be on the left side, or they might overlap, as we can see on the third picture. And finally, they might even overlap completely. So in cases where the boxes overlap perfectly or have the same value for a particular coordinate, the minimum or maximum operation of comparing a value with itself is simply the value itself. So we didn't consider before the values might be different for different coordinates, but when they overlap, the minimum and maximum value of the same values will return that value again, which is 1. Now that we have the coordinates of the intersection, we can figure out the area of the intersection and the area of the rectangle formed between box 1 and box 2. In practice, we would take the modulus of the width and height so that we don't want negative width and negative height. So to make sure that even if the orders of the boxes are changed, the width and height would still be positive. And previously we have computed the point x inter 1, y inter 1, x inter 2, y inter 2. And if x inter 1 is greater than x inter 2, we would still get a positive value for the width. So even if we change the position of the boxes, if we use a modulus in order to compute the width and height, because we need x inter 1 might be on the left or on the right, so we need these values to be positive. So we have to take the modulus. So in order to calculate the area of this intersection region, first we have to figure out the width inter, and it's just the difference between x inter 2 and x inter 1, which are the x coordinates for the top left and bottom right corners. And the height inter can be computed by just considering y inter 2 and y inter 1. And after computing these two values, we have to take the modulus of these values, and then finally we can multiply the width and height in order to find the area of the intersection. So now we have already computed the area of the intersection. The second component, in order to compute the IOU, we need the area of the union. And the union of the boxes is the total area covered by both of the boxes. So to find the total area, we have to calculate the area of each of the boxes independently. So in order to compute the area of each of the boxes, for example, for the first box, we take the top left and bottom right corners of the box 1. So width box 1 would be x2 minus x1. We take the difference between the x coordinates. Height box 1 would be the difference between y2 and y1. And the width box 2 and height box 2 are the width and heights for the second box, and they can be computed by using the top left and bottom right corners of box 2. And we find the difference between the x coordinates to find the width and the difference between the y coordinates to find the height. Once the width and height for each of the boxes are computed, we can multiply the width and height of box 1 to find the area of box 1. And we can multiply the width and height of box 2 to find the area of box 2. So if we look at the total area covered by the two boxes, we see that the portion of the intersection is covered in both of the boxes. So we have the intersection is being considered when we calculate the area for box 1 and box 2 independently. So the area of the intersection can be removed so that we can find the union between the two boxes. So since we want to account for the common area of intersection only once, we can subtract the area of intersection we calculated from the total area of the two boxes. So first we sum the area of the two boxes, and finally we subtract this overlapping region to find the area of the union. And finally, we compute the IOU by taking the ratio of the intersection of the overlapping region we computed first, divided by the area of the union, which we computed now. So what is the range of values that the IOU can have? The IOU of two boxes can have any values between 0 and 1. In case there are two boxes that do not intersect, the area of their intersection would be 0, and therefore the IOU would also be 0. If they do not intersect, they don't have any overlapping region. So the top component of the ratio will be 0, and the IOU would be 0. And in case if the two boxes completely overlap, the area of the intersection would be equal to the area of the union. So the numerator and the denominator would be equal, and the ratio would be 1. So the IOU would be 1. So now we're going to look at a code in order to implement the IOU in Python. So we can write a function, and we we compute, we just define a function known as IOU, and then we pass the coordinates of box 1 and box 2 respectively as parameters to the function. Then we take each of the coordinate points from box 1, and we take each of the coordinate points from box 2. And by using the formulas before, we use the built-in function max and min in order to get the minimum and maximum points, in order to get x inter 1, x inter 2, y inter 1, and y inter 2, just as we did before. And in order to compute the width and height of the intersection region, we take the differences between the x coordinates and take the absolute value to compute the width of the intersection. And we take the difference between the y coordinates and take the absolute value to compute the height of the intersection. Then we multiply the width and the height of the intersection region to compute the area inter. Then the next step would be to compute the union. Now we have finished the intersection. So we take the differences between the x coordinates for box 1 and assign it to, and take the absolute value and assign it to width box 1. And we also compute the height of box 1 by taking the difference between the y coordinates y2 and y1 and taking the absolute value. We also do the same for box 2 and compute the width and height of box 2. And finally, we compute the area of box 1 by multiplying the width and height of box 1. And we also do the same for the area of box 2 by multiplying the width of box 2 and the height of box 2. And then finally, after we have computed the area of box 1 and the area of box 2, according to the formula we have seen before, we add the area of box 1 to the area of box 2 and subtract the area of the intersection and assign it to the union, area union. And finally, we create a variable known as IOU, which is going to be the ratio between A inter divided by area union, and we return this IOU. So we have basically looked at how to compute the IOU and created a Python function. So this is basically what we have talked about. So the function IOU takes two boxes and both have coordinates given as x1, y1, x2, y2. We find the area of intersection followed by the area of the union. And the ABS function is an inbuilt function in Python to calculate the modulus. This ensures we never end up with a negative width or height. And the IOU returned is a value type float that lies between 0 and 1. Next, we'll be talking about Non Maximum Suppression, or NMS. Non Maximum Suppression is a technique used mainly in object detection that aims at selecting the best bounding box out of a set of overlapping boxes. So in the following image, the aim of non-maximum suppression from this image would be to remove the yellow and blue boxes so that we're left only with the green box. So the reason we need non-maximum suppression is because we can have multiple predictions for the same object. So for example, as we can see here, we have 3 predictions for the same object. And it is ideal if we only have just one box in order to depict one object. So the green box is the one that's needed. So how do we remove the yellow and blue boxes? Because they don't completely fit the region of the object. So non-maximum threshold for an image with 2 different classes. So this is an image which shows 2 objects, a dog and a person, and we have 3 prediction boxes for each of the objects, and we just want to consider the one with the highest confidence score to represent these 2 objects, and we have to remove the rest. So what's the algorithm that we can use in order to remove the rest of the boxes? So the format for each of the bounding boxes that we will use is as follows. So x1, y1, x2, and y2 will represent the top left and bottom right corners of the rectangular region. C represent the class, and finally we have a confidence. We have already talked about all of these in the beginning of the video. Now let us assume that this particular image we have has three bounding boxes, a blue box, a yellow box, and the green box, and we put them inside of a list. So we can represent the green box by using the coordinates as shown here, and the class will be a cat, and 0.9 is the confidence score. And we do the same for the yellow box and the blue box. As we can see, the confidence score for the green box is higher than the yellow box and blue box. And the class is the same for all of these boxes. So we can only compare the boxes for each class. So as the first step in non-maximum suppression, we sort the boxes in descending order of the confidences. So the green box has a higher confidence with 0.9, and the blue box with 0.75, and blue box has 0.85, and yellow box has 0.75. And once we put them in descending order, we then define a confidence threshold. So a threshold is just basically a number which we define by ourselves. It's like a cutoff point, and any box with a confidence score that's below the cutoff point is going to be removed. So for example, let us assume that we have a confidence threshold of 0.8, and using this threshold we would remove the yellow box because its confidence score is 0.75 and it's below the cutoff point of 0.8. So the first step is to remove all boxes which have a confidence score that is less than the threshold. So now we're just left with the green box and the blue box. So after removing the yellow box, we're left with the green box and blue box, as we can see in the picture below. So the second stage is the comparison of the remaining boxes. So since the boxes are in descending order of the confidence, we know that the first box in the list has the highest confidence. So we have already sorted in descending order, so the first box needs to have the highest confidence. We remove this first box from the list and add it to a new list. In our case, we would remove the green box and put it into a new list, let's say B box list new. And at this stage, we define an additional threshold. So we have two thresholds. The first one was for the confidence. The second one is another threshold for the IOU. So once we remove all of the boxes below the confidence cutoff point, we need another threshold in order to remove the remaining boxes so that we're left with only one, which is the highest. So this threshold is used to remove the boxes that have a higher overlap with the one which has the highest confidence score. So the reasoning behind it is as follows. If two boxes have a significant amount of overlap and they also belong to the same class, it is highly likely that both the boxes are covering the same object. So it would be ideal if we just select the one with the highest confidence score, and any remaining bounding box that has a high overlap with this box needs to be removed because we just want to select the box with the highest confidence score, and that's why we need the IOU. So since the aim is to have one box per object, we try to remove the box that has a lower confidence. So for our example, let's say the IOU threshold we define as 0.5. So we have two boxes, green box and blue box. So in order to have the green box only, we have to remove the blue box. So we start calculating the IOU for the green box first, and we compare it with every remaining box in B box list, which is in this case, in B box list, we have two bounding boxes. So we compare the IOU of the green box with the blue box, and after they both belong to the same object, which is a cat. In case you have multiple objects, you might have a lot of bounding boxes that you can compare with different classes, so we don't compare the IOUs for different classes. So in our case, we would calculate the IOU of the green box and blue box only. And if the IOU of the green box and blue box is greater than the threshold we defined as 0.5, we would remove the blue box since it has a lower confidence and it has a significant overlap. So when we compute the IOU between green box and blue box, let's say it came out as 0.6, and since the IOU threshold is 0.5 and 0.6 is greater than the cutoff point, that means there is a significant overlap between these two regions, and we need to remove the blue box because it has a lower confidence than the green box. So this procedure is repeated for every box in the image to end up with only unique boxes that also have a high confidence. So we have talked about the idea in general, but let's see the algorithm one by one. So first, we define a confidence threshold and an IOU threshold. So we need two threshold values. The second step is to sort to the bounding boxes in descending order of confidence. So all of the bounding boxes will be sorted in descending order by using their confidence values. Third, we remove the boxes that have a confidence less than the confidence threshold. Just as we did before, we removed the yellow box because it has a confidence score less than the confidence threshold. So that this is the third step. And for the fourth step, we need a loop. We need to loop over all the remaining boxes after the removal of the boxes using the confidence threshold. And starting first with the first box that has the highest confidence, we loop over all of the remaining boxes. And on the fifth step, we calculate the IOU of the current box, which is the one with the highest confidence, with every remaining box that belongs to the same class. So we only compute the IOU of the current box with the remaining boxes that have the same class. If any box belongs to a different class, we don't compute the IOU. And if the IOU of the two boxes is greater than the IOU threshold, we remove the box with lower confidence from our list of boxes. So in our case, when we computed the IOU between the green box and the blue box, we got 0.6, which was greater than 0.5. So we removed the blue box because its confidence was lower. So we remove all of the boxes with lower confidence from the list of boxes. And on the seventh step, we repeat this operation until we have gone through all the boxes in the list. So this is the algorithm. Now let's look at the code in order to implement this algorithm. And we're going to be using the IOU function that we have previously defined to compute the IOU, just in case you don't understand where the IOU is coming from. And let's see the code in detail one by one. So the first, we define a function known as NMS, and it has 3 arguments. So the first one would be the boxes, or the list of the boxes for a particular image, and a value for a confidence threshold, and we set a default value of 0.7. That's the cutoff point for the confidence. And the third argument is an IOU threshold, and we define a default value of 0.4, and that's the cutoff point for the IOU. Now we are inside the function. We create 2 lists called bbox list thresholded and bbox list new. And bbox list thresholded contains the new list of boxes after filtering low confidence boxes. So after using the cutoff point for the confidence threshold and removing the boxes that have a lower confidence than the cutoff point, we put all the values after filtering out all of the low confidence boxes and put them on the first list. And on the second list, which is B-box list new, contains the final list of boxes after performing non-maximum suppression. So by using the IOU threshold, we remove the remaining boxes, and then we put them inside the second list, which is B-box list new. So we start stage one by sorting so the third step in our algorithm was to sort the list of bounding boxes. So boxes was our list of boxes, and we use the built-in function sorted of Python in order to arrange them in descending order. And in this case, we define a keyword reverse equal to true to sort the list in descending order. And the second keyword key specifies the constraint we want to use for sorting. So we want to compare the confidence score of different boxes. So when we specify the coordinates of the boxes, the fifth element was the confidence. So we have x1, y1, x2, y2, and 4 points, and then the fifth element would be, and then we have the class, and then we have the confidence. So by using indexing, we just only select the confidence score of the bounding box in order to compare and sort them in descending order, and assign the sorted value to boxes sorted variable. And we iterate over all the sorted boxes and remove the boxes which have a confidence lower than the threshold we set. So we have already arranged the boxes in descending order of their confidence scores, and then we create a loop, and then it goes through all of the boxes in the sorted box. And inside the if statement, by using the fifth component, the fifth element, which is the confidence score of each of the boxes, will be compared with the confidence threshold of 0.7. And if they're greater than 0.7, we would append this box to the list, B-box list thresholded. Else, we just put a pass. We don't do anything. So this step is the fourth step in our algorithm, in which we remove all of the boxes below the cutoff point for the confidence threshold. In stage two, we loop over all the boxes again in the list of the thresholded boxes. Now we have all the boxes which have a confidence score that's greater than the confidence threshold inside of the B-box list thresholded. And then we create another loop. And first we pop the first element in the list, because since we arrange them in descending order, the first element has to be the one with the highest confidence score, and then we just assign it to the variable current box. And then we append the current box to B-box list new list, because it is the one with the highest confidence score. Then we create another for loop, and then we iterate over all of the boxes inside the B-box list thresholded list. And then now we use the fourth component, the fourth element of the box is the class of the box. So if the class of the box is not equal to the current box, which means the one with the highest confidence score, so we compare the class of each of the boxes in B-box list thresholded to the class of the box with the highest confidence score. So if they match inside the if statement, we compute the IOU between the current box and the box, which is taken from the B box list threshold. The reason we use box in brackets then colon 4 is because we just want to use the values x1, y1, x2, y2 in order to compute the IOU. So we just need the coordinate points and we don't need the class and confidence values in order to compute the IOU. And once we compute the IOU between the current box and the box from the B box list threshold, we compare the IOU with the IOU threshold. And if that IOU is greater than the threshold value, we remove the box from the B box list threshold. So first we use the confidence threshold in order to remove the boxes with low confidences. Second, we use the IOU threshold in order to remove the remaining boxes with low confidence scores and also that have higher overlap with the current box. So finally, after everything is finished, the boxes that's appended to B box list new will be the maximum one, because B box list new only contains the one with the highest confidence score. This will be the box that's going to represent our object. So this procedure for non-max suppression can be modified according to the application we're using. For example, the model YOLO V3 makes use of two sets of confidences as a thresholding measure. So this is all about IOU and non-maximum suppression, and thank you for watching this video.